name is Roshashi and my matrix number is 217178.
Hi, my name is Surendran Nathan and my matrix number is 217012.
My name is Muhammad Fazalkan bin Muhammad Razali and my matrix number is 214244. Is Edwin Hussein with matrix number 215150.
My name is Muhammad Yamsi bin Abdul Aziz and my matrix number is 214201.
So this is our full setup for water flow rate project, and our control variable is the water flow rate, and the manipulative variable will be the pump speed, and the whole setup you can see here. So this is the water source tank, and this is the storage tank 1, and this is our water flow sensor YS201, and this is our pump speed, which is connected directly to the power supply, and this is our Arduino Uno, and this is connected to the motor driver, and this is our breadboard, and the Arduino Uno is connected to our laptop with the coding. So this is the whole setup for the project.
Okay, so I will explain about coding. Let's look here. Okay, so this is the coding for the motor driver. The NA will connect to pin number 5. The IN1 will connect to pin number 3. Then our motor speed, we set the motor speed to 255 for the its maximum value. And this is the coding where the flow rate will be converted to liter per minute. So this is the coding where the unit form.
Okay, then we set the motor speed around 255 and then we need to wait until the flow rate become steady state and reach the equilibrium. Okay, now I'm showing on how to do the process identifications of the water control flow. So as you can see here, the after we turn on the pump, the water flow sensor sense from the zero flow rate to the constant flow rate. Although there is some variable deviation here, but this is because due to the magnetic flow sensor is very sensitive with the movement of the hands when we try to move from the bottle to bottle. So it will have some deviation here. But throughout the process identification, so we will detect the deviation of the error and try to see what is the best transfer function to describe this process variable. There is either f of dd, s of dd, or s of dd with 1, 0. So, but then we have to know the deviation variable between us first. So we are inquiry about the steady state changes after the pump have reached the steady state. So we will have to remove the 0 here by defining the pump have reached the steady state, which is the 1.07. So it will move these three variable here, and then we shift out this variable up to the initial time. Okay, so as you can see here, we can sort out to that the changes for the water flow against the time is already changed in steady state, but we have to define it because it is the change in variable. So what we can do is there is a deviation variable is equal to 1.07. Okay, so now we have to make a column for the y deviations. Okay, so it is equal to the y actual minus the y deviation variable. And once we get it, we can get the answers. So we can use, so remember to log it. Okay, so this is the y deviation that we have to study about the effect of the steady state with the f of PDD, s of PDD, and s of PDD with 1, 0. So you use this value to test each of the transfer functions. First, we will test with the f of PDD. So we will fill it in this column. Sorry. Okay. So now we have to define the value of m state change and as well as a k tau data as the initial case. So m we define as 0.4 because it is the maximum it reach for one it reach the steady state. So step time we define as 1, 2, 2, and 3. Okay. Now we can see the pattern of the steady state graph with the f for PDD. So we will use the solver to decide what is the sum of error square which is less. So we will take that value, take transfer function as our process transfer functions. Okay. So the error, the sum of error square for the f of PDD will be 1.825. But we have to test with another two transfer functions, that is S of PDD and S of PDD with 1, 0. So let us test this. Apply the same method for the S of PDD, we can see that the sum of error square now is 17.61. Same goes to for the SOPDD. The sum of error square slightly increased if compared to the SOPDD. There is a 18.26. So if compared with these three model here around FOPDD, SOPDD, and SOPDD with 1, 0, SOPDD is the best transfer functions to describe this process variable because it have the least sum of error square, which is 17.61 compared to the FOPDD with 18.25 and SOPDD with 18.26. So that's all for the process identifications.
This is our control block diagram. For this KM, we assume as 1, and then this is our GC, which is controller, and then the GV, GIP, and then GP, and then GM. So we assume GV and GIP is equal to 1 and GM also equal to 1. And then we are now insert the disturbance, and then this is for our GP. And then GP, this is our transfer function for the GP, and then the time delay is 0.68156694. Okay, so now I will insert the K and tau to our GC. Yeah. Our P is equal to value of K, and then I is, since we use the auto tuning, so we assume that K integral is K over tau, and then the derivative is k k multiple with the tau. And then we just press OK, and then we tune it. So this is the diagram that we have get. This is our control.